Hello, everyone. Let's take a look at the problems on the 10.3 Achieve assignment. It's pretty fun, and it's a pretty quick section. What we're talking about in this section, for the most part, are the intervals of convergence test. We use the integral test. We use the limit comparison test, the comparison test, the alternating series test. Oh, wait a minute. Alternating series test is 10.4. So we'll leave that for that section. But in this section, it's the integral test, the limit comparison test, and the comparison test. So first of all, problem one, it asks us to use the integral test. And then after that, which statement is correct for the infinite series? We have the summation from 1 to infinity of n to the negative 1/5 power. Now, I already know just by the p-series test, this would equal 1 over n to the 1/5. Therefore, this is a p-series with p equals 1/5. Diverges, period, end of story. But they ask us to use the integral test on it. So I do that. It's the integral from 1 to infinity of x to the negative 1/5 with respect to x. I went ahead and made that a proper integral and said the limit as b approaches infinity of the integral from 1 to b. Then you'll see I used the power rule on that. And we can quickly see why it diverges with the integral test as well, because when you try to evaluate this integrated expression at the limits of integration, at that upper limit that's approaching infinity, you're going to have 5/4 infinity to the 4/5 power. Well, clearly that's an infinite solution. And anytime the integral diverges off to infinity, the corresponding series diverges to infinity. So our first question there is divergent. We go on to the next one here. If I look at it, it gives me, again, it's saying the integral test to determine whether the infinite series 13 over n squared plus 1, we're asking if that's convergent. Well, okay, the integral test, you take the corresponding integral, and I went ahead and made it a proper integral, the integral from 1 to b of 13 over x squared plus 1 with respect to x. As soon as I've recognized 1 over x squared plus 1 would just be the inverse tangent of x, I know I can factor that 13 out front and then say the 1 over x squared plus 1 is the inverse tangent. 13 inverse tangent. Well, when I evaluate at the upper limit of infinity, you've got to be thinking as the inverse tangent function goes off towards infinity, what is the y value going off to? It's going off to pi over 2. So you can say, all right, the inverse tangent of infinity is pi over 2. The limiting value of the inverse tangent of 1, well, that's just at pi over 4 because you know that the tangent of pi over 4 is 1. So we get 13 times pi over 2 minus 13 times pi over 4. We know that that's going to give us a solution of 13 times pi over 4. And in this one, it wanted both answers. Anytime the integral converges to some finite number, that's evidence that the series also converges. You don't know what the series converges to, so I am not saying that the series converges to 13 pi over 4. That's what the integral converges to. All we know is that since the integral converges, the series also converges. And you'll see that's what I put here. Yes, the integral converges to 13 pi over 4. That's conclusive evidence that the series also converges. For number 3 here, we have, we're asked to use the direct comparison test. Typically, I just call that the comparison test. And it's asking us to look at the series where we have the summation of the sine of n quantity squared divided by n to the 10th. Okay, so the way I thought about that is I know that that numerator, you know the sine function always oscillates between -1 and 1. So the sine function squared would oscillate between 0 and 1. So I'm just saying I know that that numerator is always less than or equal to 1. Thus, we know that the fraction or the general term of this series is less than or equal than 1 over n to the 10th. Again, since that numerator is less than or equal to 1. Now, what do I know about the series of 1 over n to the 10th? Well, I know it's a convergent p series. Remember, 1 over n to the p converges anytime that power on that n is greater than 1. So that's what I put here. This is a p series with p equals 10. Clearly, that's greater than 1. That means that series would converge. So how does this comparison test help us? We know that the series in the problem that we're dealing with is smaller than a series that converges. That conclusively shows by the comparison test that the series that we're interested in must also converge. And so you'll see I've chosen up there that the series converges. For the next question here, number 4, I'll show my work down here. We have the series for the general term is from n equals 24 to infinity, 8n squared plus 9 over n times n minus 18 times n minus 10. Now, don't really concern yourself necessarily with where the series is beginning at. It's the fact that it's an infinite series is what we're worried about and whether it will ever converge or not. So the fact that it's starting at 24 is really inconsequential to me, other than I know that if it starts at 24, it can never take on a negative value. You would have to be wary if n started at any value, let's say 18 or lower, because at 18 it's not defined. At any value lower than 18, you're going to have a negative down there. So I can say, well, all right, don't have to worry about any of those instances since n starts at 24. Now, what I chose to compare to here when it's saying use the limit comparison test is I just said, well, I know that the degree difference in the numerator and denominator, numerator's degree 2, denominator's degree 3. So I know that this should be compared to a p series with where p is equal to 1. The degree of the denominator is 1 greater than the numerator. So I chose to compare it with b sub n equals 1 over n. Now, what does the limit comparison test tell us? It tells us that if the limit of the general term of the series that we're interested in divided by the general term of a series I know something about, if it's some finite multiple, then whatever happens to the series b sub n, that same thing happens to the series of a sub n. Okay, so I went ahead, simplified out the problem. Whenever I divide by b sub n, I'm just multiplying this series by n over 1, and you'll see that's exactly what I did. My numerator goes to 8n cubed plus 9n. Now, I know that since this is a limit as n approaches infinity, the only thing that you care about are the leading terms in the numerator and denominator and their coefficients. I'll have an 8n cubed up top and a 1n cubed on the bottom. That's going to simplify to be a limiting value of 8. Now, here's what I know. I know that the series that I'm interested in, this series right here, it's approximately going to be 8 times the size of the series of b sub n. What do I know about the series b sub n? Well, the series of 1 over n diverges. Why does it diverge? Well, it diverges because it's a p series with p equals 1. Anytime the degree of the denominator is not more than 1 greater than the degree of the numerator, that series is going to diverge. In this case, this is the harmonic series. It's the smallest divergent series. But I can say this series does diverge, and then the series that we're interested in, well, it's 8 times the size of it approximately. So clearly it also diverges. That's what I put here. Since the series of that we compared it to diverges, and our limiting value was 8, that's conclusive evidence, according to the limit comparison test, that our series in the problem also diverges. And the way that we answer that here on Achieve, notice they say ask you what you compare it to, the 1 over n. The limiting value was 8, and then that was conclusive evidence that the series of interest diverged. Now for the next question here, number 5, you'll see I already have the answer that it diverged for my problem. Let's talk about why. I'll bring this up and make it larger. So for here for number 5, what I did, I had the summation of the series from 23 to infinity of the fifth root of n over 10n plus 16. So instantly I looked at this and said, well, your numerator is going to be n to the 1/5, denominator's n to the 5/5. So if I simplified that down, I'm going to use a limit comparison test with 1 over n to the 4/5. That's the degree difference from the numerator to the denominator. Now, what do I automatically know at that point? The series that I'm comparing it to, if this were inside of a summation sign, I know that the summation of 1 over n to the 4/5 is going to diverge. How do I know that? Well, because it's a p series with p equals 4 over 5, and the test is that if it's less than or equal to 1, that fraction is going to diverge inside of a series. So now I use my limit comparison test. If I can show that this general term divided by this general term is some constant factor, then whatever happens to this series happens to this series. And I already know the series of 1 over n to the 4/5 diverges. So a limit comparison test, I take the general term of the series of interest divided by the general term of the series that I chose here, the b sub n. Whenever I simplify that out, I know I'll just multiply the original fraction by n to the 4/5 power, which is going to give me an n in the numerator. I'll have my 10n plus 16 in the denominator. Now, as n goes to infinity, you just say all that you care about is the fraction of the leading coefficients. It's going to reduce down to 1/10. So what this is essentially saying is that the series of interest is 1/10 the size of the series that we're comparing it against. However, we know that the series that we're comparing it against is a divergent series, since it's a p series with p equals 4 over 5. Now, 1 over 10 times a series that goes to infinity still goes to infinity. So that's why we say, so since this series diverges and the limiting value is 1/10, the series of interest, our original problem, also diverges here. Now, if we look at another problem here, number 6, now keep in mind that was the only thing you had to do on Achieve for this question, was just say series diverges, which I really don't like the way that Achieve does this section, because you could be using horrible notation and still get the answers right. You really should be trying to do the problems out like I am, where you show your thought and logic out properly. For number 6, I don't know, here I talk about showing your work properly, and I didn't write down the problem inside the summation. We had the summation from n equals 1 to 10, and then we had 1 over 0.2 to the n squared. That needs to be right here. I'll go ahead and put it in there. 0.2 to the n squared. Now, what I did is I wanted to go ahead and think about the general term inside of that series. So I took it over here to the side, 1 over 0.2 raised to the n squared power. You say, well, that's the same thing. But since 1 to any power is still 1, I can say it's that entire fraction, 1 over 0.2 to the n squared. Now, what I did with that, since every time I raise 0.2 to a larger and larger and larger exponent, it's going to make that denominator smaller and smaller. So I need you to understand that 1 over 0.2 is going to be greater than or equal to 1 over 0.2 to the n. So if I have a higher power on this one, it's going to be a greater number than this one. And you can think about that to yourself, like 1 over 0.2. We know that's the same thing as 5. 1 divided by 0.2 is 5. So you can say, well, 5 squared would be greater than 5 to the first, obviously. Now, the reason I wanted to go ahead and write it as this way is because now I can just write it as a simple geometric series then and say, well, 1 over 0.2 to the n is the same thing as 5 to the n. Now, so the original problem is greater than that, or the original general term is greater than this. What do you know about the series of 5 to the n? Well, you know it's a geometric series where every single term is successively, I should say, I'll get the word right, is increasingly multiplied by an additional factor of 5 each time. So if the first term were 2, it'd be 2, 10, 50, 250, 1,250. It's getting large ridiculously quickly. Anytime you have a geometric series where the common ratio is greater than 1, in this case 5, you know it diverges. So we have a divergent geometric series, and our series is shown to be larger than that. So that's what I said here. Since 1 over 0.2 to the n squared is greater than or equal to 5 to the n, well then clearly the series with our general term of 1 over 0.2 to the n squared also diverges. So this is using the comparison test and showing that it diverges here. So now going into achieve and seeing which one of those, notice it's the last one. We say 1 over 0.2 to the n squared is greater than or equal to 1 over 0.2 to the n, which is the same thing as 5 to the n. So this series diverges. Good problem. For number 7. Here's my work for that one. We had the series from 2 to infinity of the natural log of n, whole group raised to the 16th, divided by n to the 9 over 8. Now, this one's tricky, very tricky. One thing I need you to remember here is that every single logarithmic function is going to be smaller than any polynomial function or term, a denominator raised to any power. So I know that the natural log of n as n goes to infinity is smaller than n raised to any positive exponent, even if that exponent was n to the 0.000000001 power. As n goes to infinity, that n raised to any positive exponent is going to be larger than the natural log of n. Now, it's ridiculously hard to show, and in fact, I was trying to put numbers into my calculator, and even out to as large a numbers as my calculator could handle, this number was still larger than this. So you kind of have to just take my word on this one that this function will be larger than this function as n eventually goes off to infinity. Now, if you do that and then you say, well, all right, if we're supposed to just believe it to be true that this is larger than this, how do we work the problem? Well, then it's pretty straightforward, because all I need to do is say, well, if that's smaller than this, now notice I can plug that into your problem and say, well, what if I had the series n to the 1/10 over n to the 9/8? I know that that's a convergent p series. How do I know that? Well, because the degree or the power of that p series, the p value in it's going to be 9 over 8 minus 1 over 10. P is the degree difference from the denominator minus the numerator. And I can say, well, 9 over 8 minus 1 over 10, that'd be 9 over 80 minus 8 over 80 reduces down to 41 over 40. And I know that 41 over 40 is greater than 1. Please remember, the test for p-series test is that anytime p is greater than 1, it will converge. If p is less than or equal to 1, it diverges. So we can say, all right, then this is a convergent series. I know that the natural log is less than this numerator, so it's even smaller than this convergent series. Then the logic is, by the comparison test, we have shown that since this is smaller than the general term of a convergent series as n goes to infinity, then the series that we're interested in also converges, and this would be by the comparison test. Now, for this one, I don't think it asks us to do anything else other than just say series converges. For number 8, it did ask us to do a little bit more. Let me show you my work for number 8. We had the series 14 to the n power divided by 15 to the n power minus 2n. Now, I would have initially, no matter what they asked me to do in this problem, I would have already initially thought to use the limit comparison test. Why? Well, the comparison test wouldn't really be helpful here. And the reason it wouldn't is because I'm looking at this and seeing that, well, 14 over n over 15 to the n, I know that that would be a convergent geometric series with r is equal to 14 over 15 if it didn't have that. But this denominator is always going to be slightly less than the denominator of 14 over 15 to the n. So that makes this fraction larger. Does it help to show in the comparison test that you're larger than a convergent series? Unfortunately not. So the comparison test would not help in this problem, but the limit comparison test does. I still compare with the geometric series 14 over 15 raised to the n. The reason that that's an excellent comparison is because I can quickly and easily see, well, the r value is going to be 14 over 15. And anytime r is less than 1, your geometric series is convergent. So each term is always going to be multiplied by 14/15ths of the term preceding it. It's going to get smaller pretty slowly, but it's still going to converge. Now, in order to show that the series of interest also converges, I use the limit comparison test and I say L is equal to the limit as n approaches infinity of the general term of the series of interest, we call that A sub n, divided by B sub n, the series that I know something about. And I went ahead and wrote it as 14 to the n over 15 to the n down there. Now, I know if I divide by a fraction, I multiply by that fraction's reciprocal. That'll give me 15 to the n times 14 to the n in the numerator. And I'll have the 14 to the n distributed throughout this denominator, and I still have the limit as n approaches infinity. If I look now, you could say, well, you've got 29 to the nth power in the numerator. You'll have a 29 to the nth power in the denominator as well, and then minus 2n times 14 to the n. That 14 to the n is tiny in comparison to the 29th to the n. So we only need to worry about the largest term in the numerator and denominator, and it's the exact same thing. So you say, well, okay, as n goes to infinity, I'll have 29 to the n over 29 to the n. It's going to reduce down to 1. Well, what does that mean? It means that essentially the series of interest is just the same size as this series. Well, this series converges, therefore the series we're interested in also converges. That's the logic of the limit comparison test. So we say, since the geometric series 14 over 15 to the n converges, and the L value from our limit comparison test was 1, that shows that this series is essentially the same size. Well, then it also converges. Now, when I chose the correct value here on achieve, notice it's telling you or asking you to choose the one that says the limit L equals the limit as n approaches infinity of A sub n over B sub n. We did that. We showed that it's greater than 0, well, and it was exactly 1. Now, remember, you need to show that it's greater than 0, but strictly less than infinity. We did that. And then, so by the limit comparison test, this series converges. Absolutely. Now, this shows the other side of the limit comparison test, and this is where some students get so confused. They'll be like, well, you got L is equal to 1 in this problem, and you said it converges. In this problem, you're saying L is equal to 1, and it diverges. It's all in a matter of what you're comparing it to. So please, please make sure you understand the difference here in number 8 and in number 9. Number 9, my original problem is the series 6 raised to the n power divided by 5 to the n power minus n. So I'm saying I want to use the limit comparison test with a series 6/5 to the n. What do I know about that series? I know that each term is always going to be multiplied by an additional factor of 6/5 as it grows, sorry, as it keeps going. Well, and it will keep on growing too, and that's the problem. If each term is always multiplied by an additional factor of 6/5, it's always going to get larger and larger and larger. It's going to diverge. Now, so we say it's a divergent geometric series, and the rule for that is anytime the R value, in this case it's 6/5, if that's ever greater than or equal to 1, your geometric series diverges. So what the limit comparison test is going to tell me is that if I can show that L, which is equal to the limit as n approaches infinity of the general term of the series I'm interested in, divided by the general term of the series I know something about. If this is some constant multiple, whatever happens to this series must happen to this series. And that's what I'm going to show here. So when I did this division, I said, well, then that's the same thing as multiplying by 5 to the n over 6 to the n. I multiplied by 5 to the n in the numerator, multiplied the denominator by 6 to the n. Similar to the last problem, I can see, well, in my numerator, I'll get a 30 to the n. My denominator would be a 30 to the n. And then I would have minus a smaller term. As n goes to infinity, you only need to worry about the larger terms, and they're the same in the numerator and denominator. So this is going to reduce down to a limiting value of 1 here. And then I can say, all right, if that reduces to a limiting value of 1, what do I know? I know the series I compared it to diverges. Therefore, the series I'm wanting to know the convergence of also diverges. So please notice my notation there. I said, since the series 6/5 to the end diverges, and the limiting value from our limit comparison test L was 1, then the series of interest, 6 to the n over 5 to the n minus n, also diverges. And that's what I did here. Let's see that. You'll notice, oh, and it just simply, the series diverges. They didn't have us really think about it too much here. This next one, a little tricky, but that makes it fun. So when I looked at this one, honestly, I saw the 1 over n minus 16n. Honestly, my initial thought on this one would that it would be similar to a p series p equals 1 and diverge. It's not true in this case. And so in order to determine the convergence of it, what I did was the integral test. I said, so if I'm given the summation from 3 to infinity of 1 over n times the natural log of n to the 4th quantity squared minus 16n. So I wanted to go ahead and create a function in terms of x and integrate that from 3 to infinity. So IT stands for integral test. And then as soon as I saw this, I was pretty confident that I needed to get rid of that natural log of x in there. So that's what I did. I said u can equal the natural log of x. And then derivative of u is going to be 1 over x dx. Now, please be careful. There is a factor of x. Since x is a factor in the first term and second term, I have a factor of 1 over x dx. So when I do my substitution in the next step, that 1 over x dx will become du. And you'll notice I've completely eliminated that factor of x in the denominator. It's no longer there. It's because it went out with the substitution. Now, what happens to the natural log of x to the 4th quantity squared? Well, the natural log of x to the 4th, we know is the same thing as 4 natural log of x. And that would be equal to 4u. Well, the natural log of x to the 4th quantity squared would be 4 natural log of x squared, which would be 16 times the natural log of x squared. Okay, now I need to change my limits of integration. U evaluated at 3 would just be the natural log of 3. If you plug in infinity, the natural log of infinity, still infinity. So I come down here and I can say this integral, and I'll use proper notation and say the limit as b approaches infinity from the natural log of 3 to b. And now, where did this on the inside come from? Please remember, the 1 over the factor of x times dx all became du. This group squared right here, that was my 16 natural log of x quantity squared, which becomes 16u squared. So I have the 16u squared minus 16. Now please notice what I did from this step to the next. I factored out that factor of 1 over 16 out of the fraction, and then I would have been left with u squared minus 1 in the denominator. U squared minus 1 factored to u plus 1 and u minus 1. And then I can say, okay, I have u plus 1 over u plus 1, u minus 1, as soon as I saw I had those two factors in the denominator, I did the method of partial fractions down here. A over u plus 1 plus b over u minus 1 multiplied by the least common denominator, and I get 1 on the left. I'll have a times u minus 1 on the right plus b times u plus 1 for the second term on the right-hand side. Now, in order to solve for a, I let u equal -1. When I do that, the left-hand side is still -1. I'll have a times -1 minus 1. -2a is 1, thus a is -1/2. When I try to solve for b, I'll let u equal 1. And if b is equal to 1, sorry, if u is equal to 1, then I'll have b times 1 plus 1. I have 2b is equal to 1, thus b is 1/2. Now I took this information back into my problem. And I said, well, since a and b are both multiples of 1/2, let's go ahead and just factor an additional factor of 1/2 out. That's why this 1/16 became 1 over 32. And then on the inside, and I'm still, my limits of integration are with respect to u. On the inside, the first term, a, would be a -1 over u plus 1. I got that. And the b is going to be a +1 since you factored out that 1/2. It's going to be a 1 over u minus 1. So now I already know how to integrate both of these. This is going to be the natural log of u minus 1. This would be minus the natural log of u plus 1. Instead of writing it as that, I went ahead and wrote it as a fraction and just said, well, the positive term is a natural log of that term in the numerator. And then the minus, if I condense it, it's just going to be the natural log of that term in the denominator. So I have the limit as b approaches infinity of this natural log evaluated from natural log of 3 to b. So final step, when I try to plug in b as b approaches infinity, you're just going to have a number approaching infinity over a number approaching infinity. We know that that's going to reduce down to 1 because you take the fraction of the leading coefficients, and the natural log of 1 is 0. So my whole first term, that's nothing. But my second term, if I try to plug in the natural log of 3, I would get the natural log of the natural log of 3 minus 1 over the natural log of 3 plus 1. I got this. And that's some ugly, irrational number. I just used my calculator and found out that it came to be 3.508. It was actually a -3.508, but of course we're subtracting it, and that makes our final answer positive here. Now, do I really care what the specific answer is? No. But what I do care is that I know that the integral has a finite number that it's approaching. So since the integral has some convergent finite solution, that means the corresponding series must also converge to some number, and that's what the invergence, that's what the integral test, the invergence test, that's what the integral test is going to tell us in this problem. So you would say, since the integral converges, the corresponding series must also converge. And that is the logic of number 10 here. And again, Achieve robs you of the ability to show all that beautiful work because they just have you select one little answer there. Similarly, on the next one, they just have you select one little answer, but let's show the gorgeous work that gives you that answer. And this one's actually not that gorgeous. It's kind of easy. If we think about this one, we have the summation of 41 plus -1 to the n, all divided by n. So instantly, as soon as I saw that, I just thought, okay, that -1 to the n, sometimes it's a 1, sometimes it's a -1. So that numerator, sometimes it's a 42, sometimes it's a 40. It's either 42 over n or 40 over n, 42 over n or 40 over n. All I needed to do is just show that, well, then clearly this fraction is always greater than or equal to the minimum this fraction could ever be, 40 over n. You say, okay, since this is always greater than or equal to this, and that's clearly true because the minimum it could be is anytime n is an odd number, then it will be a 40. When n is an even number, it'll be 42. So it's greater than or equal to this. What do I know about the series with 40 over n on the inside? It's a divergent p-series. You could say, how do you know it's a divergent p-series? Well, because the degree of the denominator is 1. This is a divergent p-series with p equals 1. Now, we know our series is larger than that divergent series. Well, that's clear evidence that our series also diverges, and this would technically be by the comparison test. Sadly, they don't ask you what test you're using in this problem. It just asks you whether it's diverging or converging, and that one diverges by the comparison test. For the next one here, number 12, they gave me the series 2n plus 1 over 5 raised to the n power. All right, so what I did there, yet again, I'm using the comparison test. I'm using the comparison test because I know that the linear function 2n plus 1 would always be less than the exponential function 2 raised to the n power. So especially as n gets large, the 2 to the n is way larger than little 2n plus 1. Okay, now since this numerator is larger than that numerator, I know this fraction is larger than this whole fraction. Well, what do I know about the fraction 2 to the n over 5 to the n? I know that it would simplify to just be the summation of 2/5 raised to the n power. And then I know, hey, that's a convergent geometric series with an r value of 2/5. All geometric series converge if the r value is strictly less than 1. That's just telling you that each term is getting smaller and smaller and smaller. In fact, it's getting multiplied by a factor of 2/5 each time. So I know that since this is a convergent geometric series, and the general term of the series we need to know something about is smaller than that general term, well, then our series also converges. So we would say, since the geometric series converges, our series also converges by comparison. And you'll see that that's what I did here for that one. The series converges. For the next one here, this one moves back to diverges, but why? Oh, yeah. When you think about this one, I just used the divergence theorem on this one. We have the summation of n divided by 3 to the negative n plus 8 to the negative n. So when you think about this problem, it should be extremely obvious. That numerator is getting larger and larger and larger. It's going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, all the way off to infinity. Meanwhile, that denominator is getting smaller and smaller and smaller. It would be 1/3 plus 1/8, 1 over 9 plus 1 over 64, 1 over 27 plus 1 over 576. It's getting small, and it's getting small fast. Okay, so since I know it's going to diverge, I use the divergence theorem. What does the divergence theorem tell us? It tells us that if the limit as n approaches infinity of the general term is not equal to 0, then it diverges. Not only is ours not equal to 0, it's equal to infinity. Because your numerator is going off to infinity, your denominator is going off towards 0. So you say, well, that fraction is going off towards infinity. Therefore, our series diverges by the test for divergence, or you could say the divergence test. On here, you didn't have to say either one. You just had to know it diverges. The last problem here, it's kind of cool. I liked it. It gave me the series e to the n over the group 1 plus e to the 4n raised to the 8p. And we're supposed to solve for the values of p that will make this series converge. Okay, so as soon as I see that that numerator has a constant base and a variable exponent, I can say, okay, this has to be a geometric test. So I took the general term of the series that I have that I'm supposed to be interested in, and I tried to turn it into a geometric series. And I said, well, it's a geometric series if I just ignore that denominator, that one term in there. So this denominator is smaller than this denominator, which makes this fraction larger than this fraction. So I said, well, the general term of the series that I'm interested in is less than or equal to the general term of e to the n over e to the 4n raised to the 8n. Now, the reason I can say that this is going to be a geometric series is because I can simplify it and say, well, 4n times raised to the 8p power, that's going to be 32 to the np power to power, you multiply. And then in order to get that to look more like a geometric series, you say, well, you need to see what your general term r value is that you're constantly multiplying in. Well, then raise the whole group to the n power, and that n goes out in the numerator, and you say, okay, that's e to the n. Your denominator is going to be e to the 32p, and keep in mind, I haven't changed a thing. If you raise that to the n, you'd still get 32 np power. But now that it's written like this, I can say, okay, this would be the general term of a geometric series where the r value is going to be e over 32p. Well, what do I know about a geometric series? I know that they only converge if the general term r is less than 1. How can this general term be less than 1? There's only one way. And this, the power on the e in the denominator would have to exceed the power on e in the numerator. That's where this logic comes from. So in order to make this r value less than 1, 32p had to be greater than the power on e in the numerator, had to be greater than 1. So then p has to be strictly greater than 1 over 32. And as long as p is some number between 1 over 32 and infinity, your r value in your geometric series is going to be less than 1, which would make that geometric series converge. And then our corresponding series that we have, which has to be less than that, would also converge. It's a gorgeous problem there. And you'll see I have that 1 over 32 to infinity for my solution set for p for my problem, and Achieved liked it. Hopefully you're thinking like me, and you're thinking that this was a really cool section. Pretty fun stuff. I do think that Achieve kind of robs us some of the fun of it because you can get some of the answers without technically showing out the work. I hope you are showing the work like I am so you can develop the skills and the logic required to do these summation identities and summation convergence divergence tests rather than just taking a ballpark guess on a problem and lucking out from time to time. All right, guys, so next section will be 10.4. It's a really quick section talking about the alternating series test.